Welcome to the Bytecode. I'm Rosh Shafu, and today's episode with Antonio is going to walk us through size. Antonio, thanks for taking the time.
Uh, Thank you. Hi, everyone. I'm pleased to be here. My name is Antonio. I'm a security researcher. I've been working with audits and fuzz tests for the past couple of years, and I've been working on size for the past 6 months. And size is a credit marketplace with unified liquidity across maturities. That's um, our elevator pitch basically. And in general, size is a lending marketplace, a peer-to-peer lending marketplace with fixed rate loans. And so it's similar to Aave or Compound for those who are familiar with, but the idea here is that borrowers and lenders get matched against each other, and they can define the terms of the interest rate that they want through an on-chain order book. So basically, there is an on-chain order book. Borrowers, they submit limit orders for their loans. Lenders submit limit orders for their loans. And then they can submit market orders to match against the other party. So if you are a borrower, you can pick a lender on the order book. If you're a lender, you can also pick a borrower on the order book. And there are a bunch of other mechanisms to allow for early exits. So borrowers, they can, if they want, they can like repay their loans earlier or appoint another borrower. They can pay a bit more, maybe if they are depending on the market rate, to do an early exit. Then lenders can do the same thing. They can do an early exit and get a bit less than what they would if they would wait until the term of their loan. So we allow for early exits and also for other interesting mechanics with the accounting that we did. So so this is the README. So currently there is only one pair. So now I'm going to also explain about why we decided to implement some of these, some of it this way, and the specifics of the design decisions of the protocol, which I think is very interesting, especially for developers, because when you are developing a protocol, there are usually some trade-offs that you need to make. So here I'll also explain the trade-offs. So we decided to start with only Ether and USDC as the supported pair. And the reason is that we think this is like the biggest market for lending protocols, and also because this is the first version of size. We also are already starting to develop the next version, which will be more generic. But we wanted to test, get some feedback and start with something simple. So it will be deployed on Base, also mainnet. That's our plans. And here are some audits. It's currently undergoing a Code Arena audit right now until July 2nd. Here's the white paper. So these are already some of the decisions about the architecture. We inspired very heavily on DYDX protocol, like the architecture, and like when we were considering different types of architectures, like we took a look at like Uniswap, Aave, like the blue chips, but this version of DYDX was very interesting because it was very modular and very easy to understand from our point of view. And they also implemented because of the architecture, they also implemented kind of by default this FryPy pattern that was went out some time ago about basically validating the input explicitly, then executing the function explicitly, then validating some post conditions explicitly later. So as you see, our functions are like that. Let me show you. So this is the main entry point. So here, for example, let's say withdraw. So basically, when you withdraw money from the protocol, we do some input validation. then we execute the function withdraw, then we do some invariant checking. So the user should not be liquidatable if they are withdrawing money. Then for all the other functions is like that. Like we do a validation, execution. Some functions do not have post execution, post validation, but others have. Like for example, during a liquidation function, we check that the liquidator has gained the profit that they expect, so that they don't accidentally perform an unhealthy liquidation, like unprofitable liquidation. So yeah, so basically there are these validation, execution, post-execution, and
Yeah,
yeah, a
Antonio,
nice, yeah, please.
this is yeah, this looks super clean, man. What was the pattern called again? I've never seen it implemented
Yeah,
like this before.
it was. I'm going to show first this post about Nation, where basically they shared a different mechanism to implement the checks effects interaction pattern, which they called FryPy. There's some discussion about whether this is completely new or not, because this is very similar to the checks effects interaction. So, but I like the idea of, in the end of, because basically function requirements are checks, effects are effects, and interactions are interactions. But in addition, you also have protocol environments. So there's this PI here in the end, and basically they say how you check, for example, in Uniswap, that the x times y equals k is not changed, and they also oh, by the way, I think was yeah, this is actually from the DYDX, I guess. But yeah, basically you verify the input, then you run your actions, then you verify the final state. So this is the general idea of all interactions, basically. There are some minor concerns about like gas, because basically you are performing these invariants on every call, but they say, okay, yeah, don't worry about that. You should be worried about security.
The, the
And
first point is good. You know what else is inefficient? Having to send North Korean hackers messages via e-system.
yeah, exactly. So it's more important that your protocol is secure than it's highly gas optimized. So focus on that first. And yeah, and I'll later show how this idea of doing these invariants inside the function makes it very robust against some forms of attacks. And there are other protocols that do this very well. For example, Liquidity for LUSD, inside their code, there are some invariants inside the functions. So basically, like, there is no way you can break this, because it has been checked on every call. So this is very strong. So basically we did this way, like validation, execution, invariant. And yeah, so because of that, I'm already going back to the code. Because of that, we also decided, so one problem is obviously that we have a very huge contract in terms of code size, because all the functions would have these validation, execution, post execution. So we made use of libraries for everything. So for example, the deposit function is a library, the withdraw function is a library, market orders are libraries, limit orders are libraries, repayment, liquidation, etc. And yeah, and if you go here, for example, on deposit dot so there are, here is the validation function, here is the execution function, and you can basically this is the same pattern everywhere. So some it is a bit kind of, I don't know, weird that you have so many libraries using this. Like if you used abstract contract, you wouldn't be implementing it this way. But the good thing is that we can bypass the contract size limit and have a very huge contract because we're using libraries for everything. This is also similar in nature to the how is it called, diamond pattern, because with the diamond proxy, all functions they also live in libraries, and we decided not to use the diamond pattern because it was, in our point of view, it was a bit more complex than what we necessitated. So yeah, so it was like an unnecessary complexity because we didn't want to follow the standard. We just wanted something simple to extend the contract size. So yeah, so this idea is similar to FryPy, similar to the diamond storage, but we only used what we needed for the sake of simplicity and security, basically.
Yeah, Antonio, this is the first time I've
Yep.
seen, I don't think I've seen that before, using libraries in that way. This is interesting.
Yeah.
But you're only doing this to avoid the contract size limit, right?
Exactly. If we didn't have that, we would probably have used abstract contracts. But if you go here on this, like this is the code from DYDX, they also have a single, I think it's conference. They also have a single, what's it called? Yeah, a single entry point, basically. And they have like this global state, global parameter, global storage variable. And then whenever you perform an action, for example, here, I think, where is it? Implementation. Yeah, whenever you perform an action, yeah, I think that it was like the same code there on the nascent website. So they pass this storage state in the input parameter, and this is a library. And basically, this library is called via delegate call from the entry point contract. And yeah, so we are doing the same thing. Here we have a size storage contract, and it has a single storage variable called state. And this is the global state. So basically, we have some fee configuration, some risk configuration, like collateral ratio, token caps, that kind of stuff. We have an Oracle configuration, and this is the protocol data that cannot be updated by the admin. And all of those variables, they can be updated by the admin, like you can update the Oracle, the risk parameters, etc. And then there's a bunch of internal structs that we consolidate each specific concern. Like this is everything related to fees. Like there is a fee here, there is another fee here. This is the liquidation reward. There's the fee recipient, etc. And this is all the other structs. And this is so there's a single state. And as you can see here in the on the size entry point, all libraries, they apply on the state struct. So for example, when you are doing a deposit, we do using deposit for state, and then here there's the validation, and then there's the execution. So now let's talk about these validation functions and execution functions. So here, as you can see, another pattern that we used was to make sure that external functions, they all had a struct for the input parameter, because this way it would be easier to make sure how to interact with the protocol. Like there are no there is never a list of input parameters on functions. And the reason is that sometimes you can get a list that is too long, like 5 parameters, 6 parameters, or 7. And it makes it more confusing for users and APIs. So like if you have like a list of 4 uints, like how do you know that you didn't change the first one with the second one? So we decided to have a single struct for all parameters, like deposit, you have this deposit params. Withdrawal, we have withdrawal params. This function, limit order, you have limit order params, etc., like liquidation params. And then if you want to see like, okay, so what are the parameters of deposit? You just go to deposit.so, and these are the params for deposit. This is curious because it's also a bit different from other protocols that prefer to aggregate all struct in a single file, like data types.so, for example, like Aave does that. They have data types.so, and all their structs are under data type. But yeah, from my point of view, it's more confusing if you are interested in a single function. Like, why do I care about deposit parameters if I'm looking at the function liquidate? So here deposit belongs to deposit. So these are the parameters to deposit. Then there is token, the token you're depositing, the amount you're depositing, and this is the recipient of the deposit. And yeah, so here belongs the validation. In some cases, we validate the message sender. In other cases, we don't. And I like the idea of being explicit about the intents. So here, there's no validation of the sender. Anybody can deposit. Here, it's a validation for deposits of native ETH. So basically, we chose to force the user to pass token equals rep ETH if they are depositing native ETH. So if the value is non-zero, then they must pass rep ETH as token. Like the idea is not to make this confusing for users if they want to. They can't, for example, deposit both ETH and USDC all at once. They need to specify, okay, first I will deposit USDCs, then I will deposit ETH. This is just to make it less confusing and probably less buggy. So right now, as I mentioned, there is a single market, so you cannot deposit tokens different than ETH or USDC. Amount cannot be 0 because that's probably a mistake, and you shouldn't be doing anything if amount is 0. And parameter is, and you can't make the recipient the no address. That's also input validation. And then for deposit, we just, I'll go the simple path here. So we just deposit the underlying to this contract. So we do a transfer from, and then we mint a deposit token to the user. So this was also another idea that we took inspiration from others. Like this is a huge aggregation of inspirations, and this is what I think developers should do. Like pick the good ideas from others and then try to add other good ideas. But basically, the idea here, there's a post about this somewhere that I don't know where. But basically, I'll try to find it. Like MakerDAO join tokens or something like that. Yeah, I won't find it. But but the idea is that we took this idea from a post that basically explained how you can basically how you can tokenize deposits and what are the benefits of it. And I think this was initially pioneered by Maker, where they have a single entry point. Yeah, this is a bit complex, but basically they have a single entry point to make the inflow and a single entry point for outflow of tokens. And this is a bit different from other protocols. So, for example, Aave does not do it this way. Like many other protocols don't do it this way, but I think it's better because it makes for a better separation of concerns. So what I'm trying to say is, whenever you deposit Ether to size, we mean to a non-transferable version of Ether, which is called size Ether, like size Ether. Oops. Yeah. So for example, here you deposit underlying, which is equal to Ether, or rather rep Ether, and then we do a transfer from. So now rep Ether belongs in the size contract, and then we will mint you size Ether. And what's the purpose of that? The idea is that we can make sure that there's only one way that you can grow your Ether balance, through the deposit function. Like all the other functions, they rely on you depositing first. So this is interesting because, for example, if you have a loan and you are now repaying that loan, you need to first deposit USDC, and then you will get like size USDC, and then you repay the loan, and you are not repaying with USDC, you are repaying with size USDC. And like, why is that? Why don't you why don't you do a transfer from like USDC, transfer from a message sender, etc.? Like, why don't you transfer directly from repay? And the reason why is that by making sure that deposits, they all go through the deposit function, we can like validate the correctness of deposits alone, and then we don't need to worry about everything else. So basically, if deposit is working, like there are no I don't know, like rounding issues, or maybe fee on transfer or whatever, like or yeah, so maybe we can like make sure that we validate a single function and check for the correctness of a single function, and we don't need to take care of it elsewhere. So this makes the separation of concerns a bit better. And there's, like, in my opinion, and there are some contracts that do that, like some protocols that do that. So for example, MakerDAO, they have this idea, they call it join. So they have like gem join, which basically is a deposit for ERC20. They have ETH join, which is when they give you a tokenized version of raw Ether deposits, and then they have other join functions. And yeah, in our case, we do this with deposit. We give you a deposit token, like it's an IOU basically. Whenever you withdraw, we just burn. Like here, we burn size ETH, and then we give you back real ETH. That's the idea. That's the idea. And what else? So yeah, so this is how we handle. Oh yeah, just by the way, just let you know. So these tokenized deposits, they are also non-transferable. So we created this contract here, which is a simple Open Zeppelin extension, and then all transfers, they are guarded by this only owner modifier. So only the size contract can transfer it. Okay, so this is deposit, this is withdraw. What else? Let me go back to the README so that I can talk more about other decisions. Yeah, so another pattern that we used was multicall. So you are probably familiar with it in other protocols, but the point is that we have a multicall function that will execute a batch of, where is it? That will execute a batch of transactions. So basically you encode all the data that you want. For example, you want to deposit. For example, as I mentioned, for repay, you first need to deposit. So you can encode deposit USDC, repay USDC, and then let's say you want to withdraw your collateral because you are a borrower. Then withdraw USDC, withdraw Ether. You can do that, everything in a single multi-call. That's also nice. And okay, multi-call. We have also different levels of access control. That's to make sure that some functions are called by the multisig, others can be called by a bot, etc. This was another idea, like we don't allow you to withdraw native ether to prevent reentrancy attacks. And this was more like a simplification of our development process because we didn't want to worry about reentrancy at all. So I think this is also one of the trade-offs of speed and maybe security, because you can make sure that your functions are safe if you put a lot of time into it, and maybe you add some non-reentrancy in some places, maybe you make sure that checks, effects, interactions are being followed everywhere, but then you also need to test that, you also need to audit that, etc. And we decided to simplify it and do not allow users to receive native ETH so that we can rule out reentrancy altogether and basically just focus on other parts of the protocol. Okay, so another goal that we used was to make sure that the rounding was always correct. This is very hard. Like but as you know, like there are many bugs that are due to incorrect rounding. Like you can lose millions of dollars literally if you are not rounding in the right direction. And this is why we decided to use Soleidi's fixed point math lib for all our math operations. And basically we do a forced rounding everywhere instead of like rounding down, which is the default by Solidity. So here we have these helper functions for rounding up and then for rounding down. And then everywhere we always round up or down explicitly, which helps auditors and users know what they are getting, basically. So for example, here, let's go to, I think it's on the risk library. No, it's on accounting library. So here, for example, there is this function that will calculate your debt based in collateral values. So let's say you are a borrower and you owe 100 USDC. How much is that in Ether? And let's say Ether is priced at 4,000 USDC. Then basically you do the division and you do the math there. And here, since you are talking about that, you should be rounding up because basically the user would need to pay a little bit more than what they owe, so that they can't like abuse the fact that they are getting away with some dust amount because of the rounding. So here we are explicit about rounding up because this function is used whenever we need to take collateral out of the user. And basically they will pay the dust amount because of this rounding up. That's the idea here. Yeah, so this is why we round up here, and in other places we round down. So there's always this conscious decision of whether to round up or whether to round down.
Yeah, Tony, that's a good point, actually. I don't know why vectorized. Maybe it would be a discussion worth having why it's not called muldiv down. That's interesting.
Yeah, I don't know either. I think probably because this is the default behavior of division. But I prefer to make it explicit. So I
Yeah,
created like
me
a
too.
wrapper function here.
No, that
Yeah.
totally makes sense. I think other fixed point libraries have it explicitly like this,
Mm-hmm.
where it's up
Yeah.
and down by default. But I
Mm-hmm.
don't know why it's this way in Solidity. Okay. No, but
Yeah.
that's yeah, I like this.
Yeah. So we did this for all math operations. So for the Oracle, there is nothing, I don't know, very interesting here. It's like a standard chain link integration, basically. And what else? So this was also interesting. I'm very proud of it, and I think yeah, maybe projects will start doing this more often. But I think it's nice if you can see the coverage right at the README of a protocol, um, so that you can like basically verify, yeah, how well basically the project is doing. And usually projects, they integrate with coveralls, and I think I don't know exactly why we didn't do coveralls. I think it's because the project was still closed source, and yeah, we didn't want to integrate other services, I guess. So basically, I did this like through the CI. So basically, the CI calls coverage, and then it just spits the coverage report here. But this was also another idea that I think is beneficial, or of basically being explicit about your logical test coverage. Because here you can see very clearly about the lines of code covered. So for example, here on size.so, there's 100%. So you may, okay, so this is, I don't know, you are testing everything. But then in reality, some scenarios, they are much less tested than others, and that's part of the development process. Like for example, we have only I don't know, only 5 tests for deposit, and we have like 10 tests for market orders here, this market order, and this for the lender. And then we have 12 tests for the borrower market order. And I think this is useful. This is useful because you can see, yeah, basically your test coverage from a point of view of different functions, and not only from the lines or branches that your tests are doing. And this is also helpful because you can also expand on different scenarios. So you're like, okay, maybe there are very limited number of limit orders tests, only 4. Let's try to expand this. Then we have some invariants that can be like, yeah, maybe too extensive to talk about the invariants, but we can do that later. But basically, I also added that on the README. We have a bunch of a list of properties for the protocol, and also tests for these properties. We also did some HALMOS tests for one tricky math function, a binary search algorithm. So we verified that with HALMOS. And this is the list of known limitations and known issues. Yeah, and that's the end of the README. So I think this is the most yeah, the most important design decisions, and yeah, the most generic ideas of the system. Should we talk now about yeah, any particular user flow or test case, or yeah, something particular? What do you think? Like all the rest that I've mentioned is very generic, but we can get more specific if needed.
Yeah, let's look at testing,
Testing. Okay.
like an end-to-end
So
test or something.
okay. So let me begin about a base test contract. This is like all tests. They not all, but all, yeah, all tests that are not pure library tests, they inherit from base test, and this basically deploys the whole protocol, and then you test a specific scenario. So here we have a bunch of actors like Alice, Bob, Liquidator, etc. Then we have some helper functions to mint tokens, approve tokens, etc. This is interesting. Like we have a function to fetch the current state of all actors, And this makes the comparison like from what you are expecting and what you get a bit easier. Like let's go to like deposit test. So let's go here, for example. A deposit's very simple. I think we might have a withdraw. No, let's go to let's go to a loan. Yeah, so for sell credit market. So for example here, like let's so basically this is a test for the sell credit market function, which is a function used for borrowers to actively take a loan from the order book. So think about a list of lenders. There are a bunch of lenders on the order book, and then the borrower will pick a specific lender. They will pass the duration of the loan. They will pass how much they want, etc. And this is like this is extending from base test, which will on the setup deploy everything. So yeah, this is just a local deployment. We deploy a mock price feed, some mock tokens, some configuration parameters, and then we do an initialize because this is a proxy contract. And then we do we set up the labels like Alice, Bob, etc. And then yeah, so here we describe a scenario like Alice is depositing 200 USDC, then Bob is depositing 100 Rep ETH. Alice submits a limit order to lend, so they will submit the parameters like the maximum timestamp, a yield curve with a helper function, and then what I mentioned about having this auxiliary function to fetch the state is that we can like basically snapshot the state before and after, and then compare the properties. For example, here Alice is the lender, right? So the lender USDC should have been decreased by the borrow amount minus the swap fee. So basically here, the fees are also going, they are being sent from the lender to the fee recipient. And then here we just check that the borrower received the amount that they borrowed. So these are some very simple checks. And then we extended a bunch of these with also fuzz tests to do the same thing. For almost all tests, like this one, very simple. We have a fuzz test with like arbitrary input parameters. And then we check the same thing basically, but in a more parametric way, more general way. But we don't have that for all tests. Like I think that should be the goal for protocols. But the reason why we don't have that for all tests is because sometimes the input parameters, they may result in errors that they are expected because you are talking about maybe the input validation, like maybe the fuzzer would set it to 0, maybe the fuzzer will set max uint or whatever, so you have like some overflows, some underflows, and you are not interested on that on those scenarios. So it can be very time consuming to keep track of what errors are expected and what errors are unexpected. So in some cases, what you can do is do like a try catch and then ignore errors. I have some in some places. Like what you can do is do a try catch and ignore errors. For example, I have in other places. But another idea that you can do is do a try catch and then make sure that the errors are only the ones that you are expecting. So for example, here I'm expecting an error that you are trying to borrow more than the other party has, or maybe you are trying to borrow more money that you have, so you don't have enough cash, or maybe the other party doesn't have enough money to borrow, basically money to lend. So yeah, so that's another way to see it. And I think both has pros and cons, and more specifically in terms of the time that you're putting into these tests. Like if you try to make everything very, very generic, you will inevitably spend more time on it. And yeah, and basically the idea is that whenever you're spending time on something, you're not spending time on something else. So you need to make a judgment of when to do these extremely generic tests or maybe less generic tests. And this is like up to the developer to really decide what's the best way for them to use the test. My recommendation, which is what we try to follow, is like do some hard-coded tests. Like for example, here you're borrowing 100 for 1 year, etc. But also do fuzz tests, like do both, like not only fuzz tests. And I think the benefit of hard-coded tests is that they are easier to explain. Like you can explain them to whoever you want. Like here, you're borrowing $100 for 1 year, and you are paying like 3% on top of your of interest. So they are very easy to explain. Also, they serve as documentation because you can later like port it to a README or like a non-technical documentation, and you can have both the non-technical documentation and the technical documentation aligned. So I think hard-coded tests are very useful. But then also have fuzz tests, because then they can catch bugs. They maybe catch rounding errors. They maybe catch incorrect assumptions that you have. They maybe will show you some bugs that you are not expecting. So yeah, we always try to do both. And I think the organization of tests here, they are also yeah, a bit opinionated. Like here, as you can see, what we tried to do was to create one test file for each action that we have in our system. So as you can see here, like these are all our actions on the sites protocol. So yeah, you can either see them through here, like you can deposit, withdraw, sell credit market, this is to borrow, sell credit limit, like a limit order to borrow, same for lend. Then you can repay, you can liquidate, you can compensate that with credit. That's very specific, but basically that's another idea. You can change the user configuration, you can do a multi-call. So there are all these actions, and they are all one function. And there are also some admin functions like pause and pause. But basically, yeah, you can deposit, withdraw, limit orders, market orders, repay, liquidate, etc. And what we tried to do was to create one test file for each of those actions. So here, limit order, then there's everything related to limit orders. Market orders, everything related to market orders, deposit, etc. So the good thing is that it's easy to access any file that you want. That's a good thing. The bad thing is that sometimes you have scenarios that they are dependent on all these actions, like especially complex scenarios, like maybe the user deposits, then they withdraw, then they supply cash, then they do a bunch of weird things, and you're trying to validate maybe some security bug. And these tests, they don't fall anywhere in this simplistic like categorization. So they just feel a bit off. So perhaps we could have had some other files to host these tests. But usually what we did is just to put, yeah, basically like anywhere. So we call this, we have some scenario tests, which are, oh, actually strategy. They are tests, they are actually user stories that our protocol designers and product designers, they thought about and these are like realistic scenarios. These are how we believe the protocol will be used. So maybe there's a speculator. This is like a user that wants to lend at high interest rate and borrow at low interest rate. So they are speculating on the interest rate of the market. Yeah. So maybe they will lend at 6% and then borrow at how much they'll borrow. Yeah, five. Then there's someone else borrowing for 4.5%. So they are lending high, borrowing low, and this is like a specific scenario, like with hard coded input values, and we just added them like I don't know anywhere. And another thing that we did for this separation of tests was to put the input validation in a single file, which I think I regret. If I was doing this again, I would probably not do it this way, because I think input validation is also relevant for the context of the action that we're testing. But these tests, they are usually very, very dumb. Like I don't know, like you pass an array with length 2 and then an array with length 1, and then you validate that there's an error, like arrays mismatch. And sometimes as you are developing, if it feels like you are creating this test just for the sake of increasing your coverage, like because you know that like if you have the test implemented, you know that this will break. Sorry. If you have the input validation correct, you know that this test will break. But at the same time, you don't want to leave the door open for maybe a refactor or maybe the same bug to happen in another place. So it makes sense to add these tests, I think. But they are very, very simple. And they are also like, if you are like, as I mentioned, if you are writing this test, you are not writing another test. So time is always a limited factor, a limiting factor. So this is why I think it's tricky. Like how far you want to go on the coverage. Like if you go to 100% coverage, you may not be spending your time on invariant tests, or you may not be spending your time on documentation, or maybe you have like 5 years and yeah, you can do everything, but maybe it's like a hard judgment of how to spend your time. So basically, what I chose to do, which I think I regret a bit, was to put all input validation in a single function. So here you have lengths mismatch, no array, etc., like a bunch of errors, and then we check for all these errors just by making sure that the test would revert. And I think the bad thing about this way that was implemented was that some tests, they become extremely large and hard to understand. So for example, and this is especially true for functions that have a lot of input validation. So take a look at this one here. This is the debt compensation mechanism. So there are like, I don't know, 50 lines of code for input validation. Like you validate the status of a loan, you validate the lender, you validate the due date, you validate the borrower, you validate the amount. So lots of input validation. And then when you go to the validation function, to the validation test, I don't know, it can get very hard to understand each one of those scenarios. And so this is as if your test case had like 160 lines, which is definitely something that's very hard to understand, like 170 lines. So I think this was not the best way to approach input validation. If I were doing this today, I would probably split it into each one of the scenarios, like validate borrower, validate loan is not active, and then I would do a validation of an inactive loan. Validate out of range tenor, and then do the same thing. So maybe splitting this validation function into multiple validation functions. And yeah, I think a good inspiration for this kind of approach, I think, was also from Sadler. I think they do it very well of specifying the different scenarios that they have for their tests. And especially with the BTT approach, you can be very explicit of the scenario that you're testing. So you can do something like, validate, I don't know, validate loan not active, not active, and then you put like a modifier when loan not active, and then you just check that that it will revert because the loan is not active. So I think this can make for the tests very more modular, I think. And I think we should like try this new approach whenever like we are developing something new. I think it's easier to understand. And yeah, so this is something that I would probably refactor. But other than that, I think I think this base test function is very very modular and great for any purposes that we need. We have all helper functions here. And we also use the same functions for invariant tests, which is also nice because we are reusing all functions. The only bad thing was the validation, I think, in retrospect, and also how to describe the scenarios more easily. That could be improved.
Nice. No, I really like that setup.
Yeah.
Very interesting.
Mm-hmm.
Awesome, Antonio. I think we're at 1
Yeah.
hour, I think. This was very interesting, man. I have the feeling it will go on for the next 6 hours. So maybe we do a
Yeah.
part 2 or something in the future. But yeah, thanks very much,
Definitely.
man. This was super fun. So you're doing the Code Arena thing. Uh, is it mainnet launch after that?
Yeah, we will do the fixes and then do we want to do like a guarded launch with
Yeah.
a limited cap, and then grow the cap as we have like more confidence, Unify, bug bounty in place, and all that stuff. But it should be live soon. I don't know exactly when, but yeah, if you are interested, I don't know, reach out and we'll give you the details. But yeah, it should be live pretty soon.
Awesome, man. Well, good luck with the launch. Good luck with the Code Arena audit. This was a lot of fun. I'm gonna put the GitHub docs, Twitter, all that stuff in the description down below. Uh, Antonio, thank you very much, man. This was very interesting.
Thanks everyone. And if you have any questions, reach out. Thank you.
Awesome, man. Then thanks guys for tuning in, and I'll see you in the next one.